Hello there. So welcome to your Monday lecture for October the 5th. Let's get started and see where we were last time on Friday. So we are looking at the stoichiometry problems, these balanced equations with mass amounts of each chemical and translating the amount of chemical used into other reagents and how much product is produced based on the molar quantities in the balanced equation. Now we've done this first one with 180 grams of ethane. So now using this same reaction, we're going to try this new amount of ethane, just 15 grams, and check out how much oxygen is used, how much carbon dioxide is produced, and how much water is produced. I'll just get some space for myself here before I start. Right, so same equation, same proportions, but we're now using a different proportion than we were the last time. So first question is, well, how many moles is 15 grams of ethane? So of course our molar mass, we had said last time, using the periodic table, for C2H6 was 12 grams for carbon. That's multiplied by 2 because there's 2 moles in the formula. 1 gram per mole for hydrogen off the periodic table. Oops. Multiplied by 6 because there's 6 moles in the balanced equation. And so we'd said that 1 mole was 30 grams. So that's a molar quantity for ethane. And normally the equation uses 2 moles, but how many moles is 15 grams? Well, we take that total mass divided by our unit mass, or molar mass. So the 15 grams divided by 30. So we have, that's a terrible 30 there. That looks more convincing. That comes to 0.5 moles, or half a mole. So it's a much smaller loading than we normally see in the equation, which is, of course, 2 moles. So how does this 0.5 we're using this time compared to the 2 moles that we normally use? It's just 25%, or 1/4 of the loading. A lot of people get confused at this point and think it's 50%. 50% of 2 would be just 1. But we've got 50% again, just a half. It's 1/4 of the original loading. 2 divided by 4 gives us a half. And so we're going to have to do this to everything in the expression. It's 1/4 of the original values. And so that 0.5 moles of ethane, C2H6, whoops. And then 1/4 of the oxygen, 7 divided by the 4. That would be 1, horrible 1 there, 1.75 moles of oxygen gas. Remember, we're allowed to have these decimal places now because we're talking about molar amounts. 1 mole would be equal to Avogadro's number, 6.022 times 10 to the power of 23 molecules. Even if we have a half mole, that's still 3.011 times 10 to the power of 23. Still billions and trillions of molecules. That turns into the carbon dioxide. 1/4 of the amount would be just 1 mole. And then 1/4 of the amount of water, that would be just, if I can squeeze it in, just 1.5 moles. So now that we have the new adjusted reduced proportions, reduced to just 25%, we can work out the mass for these proportions. Because the ethane, we already know that was 15 grams. That was how we started the question. Now oxygen, atoms is 16 grams from the periodic table. Oxygen molecules is 32 grams, 16 times 2, and therefore 1.75 times that, the 32 times 1.75, that would come to 56 grams. Again, this pad doesn't want to work sometimes. So 1.75 moles is 56 grams of oxygen. The carbon dioxide, just looking for 1 mole, that's 12 grams for carbon, 16 grams for oxygen, of course, times 2. So 1 mole is just 44 grams. Apologies for my kind of scratch handwriting here. Doesn't get any better on a computer screen. And the 1.5 moles of water, again, just think about the chemical formula first. 1 gram for hydrogen times 2, and 16 grams for oxygen itself. Again, just straight off the periodic table with a slight rounding down or rounding up if it's just less than 0.1 off the whole number. So 18 grams per mole. So 1.5 moles, 1.5 times more. We have got 27 grams. Okay. Remember, there are Chem Talk videos you can look at to do more stoichiometry problems. They're online right now. And we've also got the question of the day problems. A question of the day on stoichiometry just went up today, and there'll be another partial one later in the week. Remember, for section 1, lecture is online on Wednesday. We're back to a normal schedule of live on campus on Mondays and Fridays. Because be aware that Friday is a holiday, October 9th. That's a holiday. It's instructional education day, classes and committee meetings for instructors. So there's no class on Friday. I'm pretty sure we'll actually finish off our online content for this chapter just with our online video on Wednesday. If we don't, I'll make one and put it up on Friday morning, but you don't have to attend that, just catch up when it appears, okay? So let's take a look and see what we've got next. And we should be moving on to percentage yield. Okay, so with percentage yield, it's just figuring out how successful a reaction has been. These values we have been creating for how much product is produced each time, like our last one with the carbon dioxide and the water, that's just predicted. That's a in theory calculation. It's what we estimate to be produced if the reaction works perfectly. All the molecules colliding, our collection of the chemicals being perfect. That theoretical yield is just a representation of what 100% yield will be. But then we've often got the reality when we go into a laboratory using these proportions, and that reality often tends to be less than the theoretical yield. Maybe the chemicals don't react quite hot enough, or maybe we don't react them long enough. There's always usually some reason for not every single molecule being converted into products of the reaction. And sometimes it can just be about losing product when you're working up the reaction, not getting that last bit out of the beaker. So we've got this actual yield from when we go into the laboratory compared to the theoretical yield, and that gives us a percentage of the theoretical. Sorry, just getting a text message there from somebody at work. We'll shut that off. So a percentage tells us how much of the expected yield was actually produced. We look at an example. In industry, the production of acetaminophen is important, a billion-dollar selling drug, of course, from just about everybody in the country. Everybody has headaches at some point or fevers. And so the reaction involves this compound 4-aminophenol, C6H7NO, and that combines with acetyl chloride. They combine by kicking off the chlorine to allow attachment on this side and a hydrogen to allow attachment on this molecule. And so they free up those atoms to allow a bond to form between them, and we get the acetaminophen with hydrogen chloride kicked out as a minor side product. So a student reacts 327 grams of the 4-aminophenol in an attempt to produce the maximum yield of acetaminophen. Calculate how much acetyl chloride he would need to react with this 327 grams of aminophenol to try and get it to fully react, and then how much of the product acetaminophen would we expect to produce. And if someone went into the lab based on your calculations and only produced 302 grams of the acetaminophen, then how much would that be as a percentage of the theoretical yield? So of course our equation again is in molar quantities. 1 mole of this reacting with 1 mole of this to produce 1 mole of the product. A 1-to-1 ratio, but we need to know how many moles 327 grams is. So from that chemical formula, C6H7NO, we can work out the molar mass. 12 grams for carbon times the 6, 1 gram for hydrogen, 14 for nitrogen, and 16 for oxygen. That comes to a grand total of 109 grams. It's a little bit over, but usually just round down. And so that total mass we were told about, 327, divided by the unit mass, the mass per mole, the 327 is actually 3 moles. Now the equation normally uses just 1 mole, so that calculated amount compared to the original amount in the equation, it shows us that we've got 3 times more. 3 times the aminophenol. And so we're going to need 3 times as much of the acetyl chloride. And we'll produce 3 times as much of the product, the acetaminophen and the hydrogen chloride, which is produced as a side product. So instead of 1 to 1 to 1 to 1, 3 times more, we've got 3 to 3 to 3 to 3. The same ratios, relative proportions, will be there once you've scaled up or down your stoichiometric reaction. So now we've got a target for acetyl chloride and for the acetaminophen, 3 moles. For the acetyl chloride, we can work out the mass of 1 mole. That's 12 grams for carbon again, times 2. 1 for hydrogen times 3. 35.45 for chlorine. And 16 for oxygen. That comes to just over 78 grams. So 3 times as much. That'd be 235.35. For the acetaminophen produced, again, we're now expecting 3 moles. Work out again the mass of 1 mole, the 12 for carbon, the 1 for hydrogen, and the 14 and 16 for nitrogen and oxygen. So as we said earlier, that's 151 grams per mole. So 3 moles would be 453. If this reaction works perfectly, that's the amount of acetaminophen we should produce. But of course, the question told us at the start that we only produce 302 grams, based on the idea that somebody has gone into the lab and reported their yield. So we've actually produced 302. It was supposed to be, in theory, 453. So that's 66.7% of the 453 we expected. So these kinds of percentage yield calculations are important, especially in the money-making pharmaceutical business, because we want to produce the maximum amount of product. and therefore make maximum profits. Let's try another one. This time, a reaction between nitrogen and oxygen to produce dinitrogen trioxide N2O3. We've got 28 grams of nitrogen. How much oxygen would be used? How much of the product would be produced? And if the reaction told you that just 22 grams of the product was produced, how much is this compared to the theoretical yield? We're going to work out what percentage yield is that 22 grams. So 28 grams of nitrogen, of course 1 mole of nitrogen gas N2, that would be 28 grams, and that's the mass we have, 28. So we have exactly 1 mole. Now the reaction normally uses 2 moles. So 1 mole is just half the loading, 50%. So if we only have half the nitrogen we'd normally use, we're only going to use half the amount of oxygen and produce half the amount of product. So our new proportions at 50%, 2 becomes 1, 3 becomes 1.5, and 2 becomes 1. Now we can work out the masses for these proportions. So for the oxygen gas, of course, O2, 32 grams per mole, and 1.5 moles, that would be 48 grams. For the dinitrogen trioxide, that's easy enough. We're just looking for the mass of 1 mole. 14 for nitrogen, 16 for oxygen, so 76 grams per mole. That's our target, that's our theoretical yield. And so the actual that we were told about, 22 at the beginning of the question, divided by the theoretical, that comes to just 28.94%. 22 grams is 28.9% of the 76 grams we expect to produce. Okay, most people pretty much have that by this point. But remember, we do have some extra video online. Let's switch tacks and move to our last topic for chapter 5, very math heavy chapter, I'm afraid. And think about those redox reactions which we had touched upon in the classes of reaction earlier. We said a redox reaction was a reaction where electrons are being exchanged. There's a chemical giving electrons away, and there's a chemical which is receiving electrons. So if we look at the chemical giving electrons away, the chemical that we say is being oxidized, we sometimes see a charge become an increasingly positive charge. We sometimes see a negative charge which diminishes to 0 or becomes positive. Both things are the idea of an atom losing electrons, becoming less negative or more positive. That's an atom which is losing electrons and has comparatively more protons than electrons. And it's kind of like the ion equations we did in chapter 3 for the metals, with the electrons appearing on the right-hand side after they've been given up. But it can also be non-metals which are losing the electrons. Oxidation happens to both metals and non-metals. So the electrons lost are written on the right-hand side of the equation. If there's a chemical giving electrons away, there has to be a chemical which is receiving electrons. The chemical receiving electrons, again, can be a metal or a non-metal. In chapter 3, we strictly associated that with the non-metals because we were forming the ion for that non-metal. But now it could be a metal ion which is receiving electrons to reduce that charge or get rid of that charge in total. And when electrons are gained, we see the electrons on the left-hand side of the equation. And for every electron picked up, the atom either diminishes in its positive charge, like 2 plus minus 1 electron to become 1 plus, or becomes increasingly negative. Oxidation is the loss of electrons, reduction is the gain of electrons. And it's that exchange of electrons that drives the reaction. Now, if we look at an example, here, the reaction between zinc and copper ions, which produces zinc ions and copper, the reaction is driven by an exchange of electrons, but in the full equation, the electrons don't appear. We can just track those changes in charge to show the movement of the electrons. But that's not easy to see sometimes. And so we can break the full reaction down into two halves, what we call these half reactions, where we look at the chemical journey for each of the elements individually. So zinc becoming a zinc ion, 2 plus. Let's see where the electrons are. Likewise with the copper ions, 2 plus, the cupric, turning into copper metal. Let's see where the electrons are. Are they being lost or are they being gained? So for the zinc, of course, it's just a subatomic particle check, as we had said in chapter 3. Zinc is element number 30, atomic number 30, it has 30 protons. And because there's no sign of an electrical charge here, it must have 30 negatively charged electrons. That's the only way to get an answer of 0. However, by the end of the equation, we've got this 2 plus charge. And again, it's still an atom of zinc, so it still has 30 protons. You can't change the number of protons without changing the identity of the element. And we'll see examples like that in chapter 10. So with a 2 plus charge, the electron count must be 28. It's the only way for it to work. So we started with 30 electrons on the left. We're finished with just 28 electrons. We've got 2 electrons missing on the right-hand side. And so to complete this half equation, we add those electrons back in. They are shown separately because they're no longer part of the zinc ion. They're electrons which have been lost by the zinc. And that's corroborated when we look at the copper half reaction. The copper 2 plus, of course, the atomic number for copper is 29 because it's a 29th element in the periodic table, so 29 protons. But with that 2 plus charge, the math tells us that it must be just 27 electrons. By the end, when that charge disappears, we must have gone up to 29 electrons. So 27 to 29, we are missing 2 electrons at the start. Just like we did with the ionization of metals and nonmetals, you know you have the equation right when the electron count, total electron count in the two sides is exactly the same. So 29 to 27, we are missing 2 electrons on the left, so it also gives us 29. And so adding those electrons back on the left, remember the copper doesn't currently have them because we're showing them as a separate species, but by the end of the reaction, those electrons disappear because the copper has picked them up and put them into its shell, hence that positive charge being cancelled out. And so here's an important thing to consider with these redox reactions. Total electrons being given away by the oxidized chemical is equal to the total electrons being gained by the chemical being reduced, because it is an electron transfer from the zinc to the copper. So that's the underlying implication when we look at the original equation. Implication is that zinc, it gives 2 of its electrons to the copper, and so having lost 2, the zinc becomes 2 plus. Having gained 2 electrons, that copper charge disappears. The exchange of electrons drives the chemical reaction. Okay. Sometimes the acronym oil rig is useful for people to keep them straight. Oxidation is loss, oil. Reduction is gain, rig. So you'll always be able to remind yourself which way the electrons are heading. Oxidation is the loss, the giver, provider of electrons. Reduction is the gain, the taking of electrons. Let's look at some examples before we finish off. The other thing to quickly mention is the idea of oxidizing and reducing agents. So the zinc is giving electrons away, and it's supplying the electrons for the copper. The copper, of course, being reduced. Get my pen working here. Got a nice screen. So because the zinc supplies the electrons to the copper, we also say that the zinc is a reducing agent. Like a Hollywood agent, if you were an actor making the deals for you, the zinc is your dealer, the one that supplies the electrons you're trying to pick up. So any chemical that's oxidized is also a reducing agent. It's always the agent for the other process. So likewise, the copper here is picking up electrons as it becomes reduced. But to get those electrons, it has to take them from the zinc. So it says, thank you very much. I'll take those electrons, please. So while the zinc is providing them, the copper is also very happily and readily taking them. And taking those electrons from the zinc makes the oxidation happen. So the copper, while it's being reduced, can also be thought of as an oxidizing agent. Excuse my horrible handwriting here. They are always the agents for the other process. So anything oxidized is a reducing agent, like the zinc here, and anything reduced, like the copper, is an oxidizing agent. Okay. So let's take a look at an example here, magnesium with lead ions, the plumbus, because lead can be 2 plus and 4 plus. And it turns magnesium into magnesium ions, and the lead ions are turned into lead metal. They precipitate out on the glassware. So let's track each element on its own to create these half reactions. So the magnesium turning into magnesium ions, just as it shows us in the original equation, because magnesium is the 12th element. It has 12 protons. If there isn't any charge at the beginning, it must have 12 electrons. But because of that 2 plus charge at the end, it must have just 10 electrons at this point. So we start with 12, we finish with just 10, just a pure math of it. We're missing 2 electrons on the right-hand side. And so we can add those electrons back in to complete the half equation for magnesium. Second one with the lead, again tracking the subatomic particles. The lead 2 plus, that's an atomic number of 82, so 82 protons. And with that 2 plus charge, there must be only 80 electrons. Just a pure math of it, excuse me. Now by the end, of course, that charge has disappeared. So the atoms must now have 82 electrons. And so it's the only way to get zero charge. Proton count matching electron count. So although we finished with 82, we only started with 80 electrons. So 2 electrons are missing from the left-hand side. We add it back into the equation and we get our reduction step. 2 electrons given away by magnesium, but 2 electrons picked up by the lead. So the magnesium is oxidized and is also a reducing agent. The lead is reduced, but is also an oxidizing agent. Let's try another, just for fun. Let's see, how many more should we do? I think we'll do just this one more. That's probably what we did in class yesterday. I get my page to behave. And it might be useful to stop the video and try this with a piece of paper and pen. See if you can work out the two half equations and the species being oxidized and reduced, or the reducing agents and oxidizing agents, before we complete the answer to finish off our video today. Practice, practice, practice. Always the best solution. All right, let's take a look at this one before we finish off. And let's use blue today. Let's see also what else can we say. Oh yes, magic word for this week. Let's make it Avengers. Magic word for this week is Avengers. Excuse me. So let's take the lithium first of all. We've got 2 atoms of lithium, and this is changed into 2 lithium ions by the end of the reaction. As we look for lithium in the periodic table, it's the 3rd element in the table, and we can show that, prove it. Okay, lithium, 3rd element. So it has 3 positively charged protons in each atom of lithium. And if there's no electrical charge associated with it in the beginning, it must have 3 negatively charged electrons. Here comes my cat. Now by the end, with that positive charge, we still have 3 protons. It's still an atom of lithium after all. But with that +1 charge, the math tells us that there's only 2 electrons. So we started with 3, we've gone down to 2, we're missing an electron on the right-hand side. But remember, that's for each of those lithium atoms. There's a second lithium atom there, which must be missing a second electron. So the electrons that need to be added into the equation is 2 in total. 1 for each of those lithium ions. And of course, the electrons appearing at the end, this is when they're not part of the atom when we see them. So if they're no longer part of the atom, these are electrons lost. This is the oxidation step. Meanwhile, let's see, we choose green. Goes against my nature to use green, but never mind. We look at the iron. That starts off as, whoops, it's not 2, just a 1. The ferrous, 2+, and that's changing into iron metal by the end of the reaction, because atomic number of iron is 26, which means 26 positively charged protons. There we go. And so as we do the math once more, 26 protons, and for that +2 charge, remember this is what we did back in chapter 3, ion chemistry, +2 charge means that we've only got 24 electrons. It's the only way for the math to work. Now by the end, still 26 positively charged protons, but with no electrical charge, it must be 26 negatively charged electrons too. And so 24 to 26, we need 2 electrons on the left-hand side. And so we add them back into the half equation. These electrons seem to disappear by the end. That's because the ion is picking them up. It says, I'll take those. And so electrons picked up. This is electrons being gained. This is our reduction step. And remember, anything which is being reduced is an oxidizing agent. Anything being oxidized is also a reducing agent. It's always the agent for the other process. Just work out each time whether it's the oxidation or the reduction, and then just flip it for the agents. Okay. We don't have too much left to do at this point, it seems. Let's see, clear this. Another example down below. Maybe even try it before the online lecture on Wednesday. And a couple more examples in the next 2 pages. Then I mentioned about pacemakers, which we said could be explained by this chapter right at the beginning. And we're done. So I think that will easily be finished off on Wednesday. Very nicely too, as we don't have class on Friday. Okay, right. Stay safe, wash your hands, wear that mask properly. Avengers.